let's begin. Yeah, my name is Ruoyu. I'm a PhD student from Purdue University, and today I'm going to present DnD, Decompiling Deep Neural Network Compiled Binary. As you know, deep neural networks, DNNs, have been applied in many usage scenarios. For example, face recognition, voice recognition, healthcare, etc. And there's a trend of deploying deep neural networks on edge devices, and so there's a term called edge AI, where AI computation is done near the user at the edge instead of at the cloud. And there are several benefits of doing computation at edge devices. The first one is it has low latency. So edge AI can analyze the data locally rather than in a faraway cloud, which is delayed by long-distance communication. So it can respond to users' requests in real time. And the second benefit is it provides a high availability because it doesn't need internet access. So it results in higher availability and reliability for some mission critical and production grade application. And the third benefit is that it provides better privacy because the data collected by the edge devices are usually very private. For example, some medical data, and the edge AI enhances the privacy by containing the data locally instead of uploading the data onto the cloud. There have been some real-world cases where some products use edge AI. For instance, the NXP released an IoT solution for secure face recognition with liveness detection. It is essentially a face recognition camera that powered by DNN model and can do some authentication in a smart home scenario. And also for infrastructure, there's a company that deploy deep neural network model on a ARM Cortex-M chip to achieve remote power grid monitoring. And for healthcare, the edge AI can be used to detect early blindness and diabetic. When deploying deep neural networks on edge devices, dedicated DNN compilers such as GLOW and TVN are usually used to compile the DNN model into a binary module. And this binary module will be linked with the main program and flash onto the edge devices. In this work, we explore the possibility of decompiling those DNN binary. The DNN binary decompilation we are referring to is not just throwing the DNN binary into, say, Ghidra or IDA Pro and get tons of pseudo C code that we have totally no idea what it is doing. Instead, the DNN binary decompilation is we refer it to the process that automatically reverse engineer the DNN binary and acquire a high-level high-level representation of the compiled DNN model, including its accurate architecture and its parameters. And why we decompile the DNN binary? Why it is meaningful? The answer is that the DNN binary decompilation has many security applications. For instance, the most obvious one is DNN model stealing. An accurate and performant DNN model usually costs lots of human efforts and computation power, so essentially lots of money. For this reason, obtaining it often has high commercial value. And furthermore, the stolen DNN model can be the stepstone that turns black box attacks into a white box attack. For instance, membership inference attacks and adversarial attacks. And I will make some examples of adversarial attacks. Adversarial attacks basically is an adversary maliciously influence the predicted results of a DNN model by adding some imperceptible noises to the input. For instance, the figure demonstrates that after adding some imperceptible noises to an image of a stop sign, a DNN model will misclassify a stop sign as a teddy bear. And the figure on the right shows that an object detection model cannot recognize the people who is wearing a carefully designed clothes. The adversarial attack are huge threats to DNN model deployed on edge devices. If the attackers can acquire the DNN model, attackers can know the internal information of the DNN and conduct white box attack, which are more efficient and effective than the black box counterpart. Then you might ask, can we just use the existing compilers like either Pro or Ghidra? It turns out that the general purpose decompilers, they can only recover C language level syntactics from the binaries, but they have several limitations when dealing with DNN binaries. The first limitation is that there are lots of vectorized mathematical computations in DNN binary, and which essentially it leads to in the decompilation result, there will be lots of long loop bodies and excessive bitwise operations. Here, I show either Pro decompilation results of a single convolution operator function. It contains 348 lines of code with multiple long loop bodies and many bitwise operations. If I were a reverse engineer, I have totally no idea what this operation function do. And keep in mind that this is just the decompilation result of a single function, and a typical DNN binary contains hundreds of functions like this. And the second limitation is that the decompilation result of DNN binary varies. Decompilation result differs significantly depending on the compiler's analysis. And even with the same setup, the same compiler, same assays, and same function, but with different parameters of the DNN operator, the compilation result will also change significantly because of the compiler optimization. We will explain it later. And for the more examples, you can refer. You can check the GitHub link provided below. And the last reason is that the existing general purpose decompilers, they lack the knowledge of DNN semantics and topology. So intuitively, they cannot generate a high level representation of the DNN. Therefore, we need a new decompiler which is capable of capturing the mathematical semantics from the binary and convert the mathematical semantics into a high level DNN semantics. Before we discuss about the details of our technique, please let me briefly introduce some backgrounds about DNNs and how they are deployed on edge devices. The figure below shows a snippet of ResNet model represented with ONX format. In the figure, you can see each box is a DNN operator, and DNN operator, they are the building blocks of DNN. A DNN operator takes the output of a previous operator as its input and computes the output based on its operator type, parameters, and attributes. We will explain those terms later. And there are various types of DNN operators with different high-level semantics. Currently, there are 174 different operators defined in ONX, and the number is still growing. For example, there are convolution operator, average pool operator, and ReLU operator. Those are the very commonly used operators. And the DNN model information include operator levels information such as type, attributes, and parameters. And the model level semantics like the topology, which determine how the operators are connected. And there are two, in case of compilation schemes, there are two compilation schemes that compile the DNN model into binaries, which are interpreter-based approach and ahead of time AOT approach. For the interpreter-based approach, it generates a DNN configuration file, such as TensorFlow Lite, and there's a generic runtime library which implements every type of DNN operator. For instance, it has a convolution operator implementation and has a ReLU operator implementation, and they are generic. And during the runtime, there's an interpreter that passes the configuration file and generate a computation graph and invoke the generic DN operator implementation in the runtime library. However, it has two disadvantages when deployed on edge devices. The first is that it introduces space and time overhead because of the need to include the runtime library and to dynamically pass the DNN configuration file. And the second one is that since it uses generic runtime library, it misses some opportunity to optimize the DNN operator function given specific parameters. So there's another approach, AOT approach. It compiles, when the AOT compilers, it will specialize the operator implementation according to the attributes and parameters of specific operator instance. For example, for the highlighted boxes you see in the figure below, they are convolution 2 and convolution 3. Although they have the same type of operator, which are convolution, but because of they have different attributes and parameters, they will be compiled into two very different binary functions with very different control flow and data flow. And in another dimension, the computation backends, there are two types of backend. One is the device with only CPU, and second is the device with the accelerator, such as NPU, GPU, or even ASIC. And for the CPU-only devices, it does all the computation on the CPU. For example, there's, as we mentioned, there's a face recognition camera released by NXP, and it's all the computation happen on the CPU. And there are also some other embedded system where it needs more powerful computation power. So and they will be equipped with some DNN accelerator, such as Google Edge TPU. And in this work, our objective is to recover the DNN model in OX format from their compiled binary running on CPU-only devices. So this work we only recover the binary running on CPU devices, and how to reverse engineer the binaries running on the devices with a DNN accelerator will be left in our future work. And yeah, and our objective is our system should be generic enough to support different compilers and ISAs, and it should recover the DNN models with very high accuracy. Let me first give you an overview of our technique. So the first step would be given the DNN binary, we locate the function that implement the DNN operators. And the second step is for each located DNN operator function, we generate operator summary, which is capable to capture the mathematical semantics of that function. And the third step and the last step is given the generated operator summary, we recover the high-level model semantics and output the model in OX format. And let me give some more details about of each step. In the first step, we look for the binary function that have. In the first step, we locate the DNN the binary function that implement the DNN operator. So essentially, how we do it is we look for the binary function with certain structures. So we look for the binary function that have a nested loops and a vectorized computation. And these functions are identified as the function implementing the DNN operators. Note that our work at a binary level, but for easy understanding in the presentation, we show our running example in the source code, in kind of a decompiled source code in the following slides. In the second step, we generate an operator summary of each operator function, which can summarize its mathematical semantics. To do so, for each identified operator function, we first conduct a loop analysis to identify induction variables. We also usually call the induction variable as loop indexes. So the first step is loop analysis to identify the induction variable. For instance, in the figure below, the induction variables are the variables I, J, U, V, highlighted in the blue box. We also identify their information, such as initial value, step size, and loop count. Yeah, and for instance, for the variable I in the figure, the initial value, step size, and loop count are 0, 1, and 2 respectively. It's an easy example. I think everyone can follow it. And to identify these induction variables, we leverage some IV's properties, which they're usually initialized as a constant at a loop's entry. And these IVs determine if a loop continues. And they are incremented by a constant inside a loop. So we assume the IVs have these properties, and we use these properties to do a static analysis to identify those variables in a binary function. And with identified induction variables, we symbolize these identified IVs. For instance, the I, J, U, V shown in the figure, and we conduct symbolic execution. This step is to extract a symbolic expression that can capture the mathematical semantics of this function. And the extracted symbolic expression will represent the function's output with its input and parameters. The output essentially we define output as the memory write of this function, and input is the memory read of this function. So in this way, we can use a expression to capture its semantics. And for this easy example, after this symbolic expression extraction step, we will output a symbolic expression like this, like the one shown at the bottom of this slide. And then in the third step, we leave the extracted expression into an operator summary, represented with the intermediate representation, the IR, we design. For example, we leave the extracted expressions on the left to the operator summary on the right, shown on the screen. And where we represent the plus equal on the left to the summation function we define in our IR in the right, and replace the multiplication with the multiplication function in the right. And also we attach the induction variables information, indicating the possible values of each loop index. For example, for the variable u, its possible range is from 0 to 1, and with increment as 1. After operator summary generation, we finally recover the high-level DNN semantics. We first recover the operator type of each operator function with AST matching. Specifically, at the very beginning, we will generate a reference AST database in advance, which maps each DNN operator type to its corresponding AST. For example, here we show a reference AST model of a convolution operator. And after that, we match the AST included in the operator summary, we previously generate, and with the reference ASTs. We consider the operator type as that of a reference AST if their AST are matched with each other. For instance, here, we match the AST included in the operator summary with the convolution operator's reference AST in our database. And it is a match. So we will consider this operator is a convolution operator. And after we decide the operator type of a binary function, We then recover the DNNs topology by leveraging data dependencies between each DNN operator function. For instance, we can identify that for two operator function, we identify the input of convolution 3 and the output of convolution 1. They point to the same memory address, and so we can know there's edge from convolution 1 and convolution 3. So we draw edge and we recover the connection between these two operators. And at last, we recover the attributes and the parameters of each operator by leveraging the operator summary and the recovered DNN topology. For instance, with the operator summary, we can recover the values of filter by extracting from their corresponding memory address. And our decompiler can also correctly handle the DNN binary with some very uncommon compiler optimizations, such as operator fusion and loop unrolling. For the operator fusion, it is a common optimization technique that deployed by DNN compilers. It combines the loop bodies of two adjacent operators to improve the cache locality. And typically it combines the activation operator, for example, ReLU, with the previous operator. For instance, it is the most typical scenario where the compiler combines a convolution operator with a ReLU operator. And in the code, you can see that before this optimization, there are two loop bodies. And after the optimization, they are merged into one, and the ReLU is merged into the previous operator function. Sorry, the previous operator loop body. And to handle with the loop operator fusion, we leverage the observation that the combined set that when there's two operators combined, the second operator is usually an activation operator, for instance, ReLU. So our technique is quite simple. We first identify the activation operator in the extracted symbolic expression. So here we use some pattern matching to identify the ReLU in our extracted symbolic expression, and then we just divide the ReLU from the previous expression, and so we have two operators in our generated operator summary. In case of loop unrolling, for instance, it unrolls the loop with induction. For instance, here it unrolls the loop with induction variable v, and and this loop just disappear, and it results in two different updates. So this loop has been unrolled. So in order to handle this, we develop a loop rerolling techniques, which is essentially the compiler's optimization unroll the loop. So we, as a decompiler, we identify we recognize some pattern, and we do some rerolling to recreate a loop. And so we develop a loop rerolling analysis, which recognize the similar pattern among symbolic expressions and merge them together. For instance, in the extracted symbolic expressions, we identify the similar pattern between line 1 and line 2. And so we manage to merge them together into one expression. And our decompilation techniques can also handle composite operators. The composite operators, they are quite complicated. We will use recurrent operator as an example. So for the recurrent operators such as RNN or LSTN, their inputs can affect their subsequent their output can affect their subsequent input, so that they can exhibit some temporal dynamic behavior. And this type of operators, they are usually used in NLP model. So when these type of operators they are compiled, they are rolled out and decomposed into some basic operators. For instance, the fully connected or the ReLU or the tangent. So, and these basic operators, our decompilers already support those. So our approach is we can recover those basic operators first, and then we use pattern matching to recover the composite operators. For instance, here for given, say this RN operator. So if you roll out into a sequence of operators, and for each operator inside is essentially a composite of fully connected and addition and bitwise addition and tangenta. We identify those basic operators, and then we use pattern matching to merge them into one RN operator. And and that's basically our system design. And we implement our system with Python on top of Anger, and we reuse many Anger's components such as CFG recovery and loop finder. And our system is open source at GitHub. For evaluation, we first evaluate the generality by evaluating how many widely used DNN models we can support. We consider a DNN model supported when all of its operators are supported. We collect 37 DNN models from two benchmarks. First is ONX2, and the second is MLPerf Tiny benchmark. And it includes many widely used and famous models such as ResNet, YOLO, and GPT-2. And they cover many different types of DNN operators. Our evaluation showed that our system can support 59 different operators, so 84% of the 70 of the total 70, and we can in turn it support 30 DNN models, which is 81% of our dataset. Then we evaluate the correctness of our system by checking if our system can decompile a DNN binary and generate a DNN model equivalent to the original one. We test with 15 DNN binaries, and they are compiled by two compilers, GLOW and TVN, 3 ISAs, Ensemble, Architecture x64 and x86, and 3 models, MNIST, ResNet version 1, and MobileNet version 2. And we compare the inference results of the decompiled model and the original model given 10,000 test inputs. Our evaluation shows that our system can decompile all the tested binaries with 100% accuracy. For example, here we show at the top, we show the architecture of the original ResNet model, and at the bottom we show the decompiled model by our system. And as I can see, they have the identical architecture. And we further, to evaluate correctness, we further test these two models with 10,000 tested inputs, and they have the same inference results. In the case study, we also conduct case studies on a real world in a real-world microcontroller where a ResNet model is deployed. Essentially it's the ResNet model deployed on the NXP IMAX RT1050 evaluation board. And we show that our system can use to steal the DNN model from the board. Specifically, we dump the binary from the board and decompile with our system, and we verify the correctness of the decompiled DNN model by comparing the inference results with the original one. Besides, we also show that the decompiled DNN model can be leveraged to boost adversarial attack. With the decompiled model, we launch a white box adversarial attack and which successfully reduced the inference accuracy from 88% with the original inputs to the 11% with the white box adversarial input, while the black box attack can only degrade the inference accuracy to 57. And in summary, decompiling DNN binaries requires customized techniques with DNN specific knowledge. And in this work, we propose DnD, the first decompiler for compiled DNN models. And our system is open source at GitHub. And that's all for my presentation. Thank you. I will now take questions from the audience.